This video builds upon an earlier one that I've done which introduces windowing and zero padding, and you should really take a look at that video before going through this one. This one tries to explain why Dft Windowing works, so basically why the presence of side lobe components or terms are reduced when you apply a hamming or a hanning window, for example. Now the code that I'm using I'm going to make available up at this blog, and some of the code is tricky enough, so you're as well off to download it and go through it at your own pace. But to start off, I'm just going to create a signal X, which is a sinusoid, which is a frequency of 6.5 Hertz. The length of the signal is 1000 samples with a sampling frequency of 1000, so that signal has a 1 second duration. And what I'm doing at the very start is I'm zero padding the signal X by 99,000 zeros. Okay. Now, the reason why I'm zero padding is it's just easier to understand windowing when you zero pad, at least initially. By the end of the video I'll get to a situation where we're not zero padding, but you will find it easier to understand understand windowing if you zero pad at the very start. Now, ideally what I'd like to do is zero pad by a very large amount. In fact, ideally I'd like to zero pad by an infinite amount, but of course that isn't practical. However, you should be aware that if you're looking through some of the theory associated with this and you come across some issues, which you're likely to do if you consider this as just being 99,000, those issues should be resolved if you think about this as being zero padded by an infinite amount rather than a finite amount. Okay, so enough about that, and let's just copy this or evaluate this code here, and we'll take a look at what we get. And I'm only looking at the first 1500 bins of the magnitude spectrum. And there's the time domain signal that I've analysed. So there's our signal. It's 1000 samples long, which equates to 1 second, and we see that it has 6.5 cycles over its duration. And here's the magnitude spectrum of the zero padded signal, and we can see that it's got that very distinctive shape that we've seen in the earlier video. And what I'm going to try to do is explain why we get this distinctive shape first of all. So what we can see is we do get a maximum at bin number 650. Okay, and the frequency associated with that maximum is of course going to be the sampling frequency divided by the length of the signal, which in this case is 100,000, multiplied by 1000. So let me just write that out. So the frequency associated with that maximum is the bin number, which is 650, divided by the length of the signal that we analysed in order to obtain this magnitude spectrum, which was 100,000, not 1000, multiplied with the sampling frequency, which is 1000, and that's equal to 6.5 Hertz, which is what we expect. So what I'd like to do now is just I want to plot this magnitude spectrum in terms of Hertz rather than in bins. So if I just evaluate this piece of the code, that will do that. And we can see that all that's happened is that my frequency axis is in terms of Hertz. So we can see here that that's at 6.5 Hertz. The other thing I'd like to do is just remind you what happens when you apply a hanning window. So I'm using the built-in function in MATLAB called hanning to create my hanning window, and then multiplying the signal X by the hanning window, and I'm also zero padding again by 99,000, and I'm going to plot the magnitude spectrum and overlay it with the other magnitude spectrum so that we can compare. So what we can see here is that the original magnitude spectrum, which hadn't a window explicitly applied, is this blue shape. This is the main lobe associated with the first magnitude spectrum. We can see we also have these side lobe components here. But when we applied a hanning window function, what happens is the main lobe gets wider, but the side lobes are reduced. In fact, it's very difficult to see those side lobes. I'll just zoom in here just to show you those. So you can see the side lobe there. It is still present, but it's greatly reduced compared to the signal that hasn't had a window explicitly applied. Now, the reason why I'm saying the original, the blue magnitude spectrum, hasn't had a window explicitly applied is because implicitly there's been a rectangular window applied. Now let me just try to explain that by running through some code that I've written. Okay, so let me just, rather than going through the code, let me just select it and evaluate it, and you can go through it yourself if you want to download that code later on, and we'll see what it produces. So what I'm showing here is the zero padded signal, okay, or at least just the first 5,000 samples. Now we know that there's been 99,000 zeros applied, but I'm just showing the first 5,000 samples of the entire signal. Now I'd like to remind you again that from a theoretical perspective, if you're going through this again, you should consider this as having been zero padded by an infinite amount. Now in the middle I have this sinusoidal waveform, and again I'm just showing the first 5,000 samples. So sorry about that's difficult to read there, but that's just a sinusoidal signal, 5,000 samples. Okay, and down at the very bottom I have what's known as a rectangular window. Okay, and the rectangular window has a value of 1 up to for the first 1,000 samples, and then 0 for the rest of the samples. Okay, now a good way of thinking about a zero padded signal in order to understand windowing is to think of it as being a sinusoidal waveform, this middle waveform, being multiplied by this lower waveform, or this rectangular window function. So if you multiply that lower waveform by the middle waveform, you get your zero padded signal. And this is sort of key in order to understand what's happening in windowing. Okay, but now to understand windowing, we need to move into the frequency domain. So what I'm going to show you now is each of these time domain waveforms plotted in the frequency domain, and we will see what happens there. So let me just evaluate some of this code. Again, parts of this code is going to be difficult to understand. It might take a bit of time going through it later on, but what I'm going to do is I'm going to plot what is known as the double-sided magnitude spectrum of those time domain waveforms, and there are the double-sided magnitude spectrums of those waveforms, and you can see that we have both negative frequencies and positive frequencies shown. Now let me think. I think the best thing to do is focus in on the middle waveform first, and this is the double-sided magnitude spectrum of a sinusoidal signal. And the double-sided magnitude spectrum of any sinusoidal signal will show 2 spikes. Now each of those spikes is associated with what is known as a complex exponential. Now you don't really need to fully understand complex exponentials to appreciate this video, but I will provide a link to complex exponentials, and they are kind of key to really understanding what terms like negative frequency are. But hopefully you can gain a bird's eye perspective of what windowing is about without getting into too much detail. So let me just zoom in here first of all, just to show the spikes clearly. So there you go, you can see there's my 2 spikes associated with each of the complex exponentials, which are, the 2 spikes are located at 6.5 Hertz and minus 6.5 Hertz. Okay. The second thing I'd like you to focus in on is the shape of the double-sided magnitude spectrum of the rectangular window function. So I'm just going to zoom in on that as well now. Now we can see that it has a shape that we're used to seeing, and we saw it earlier on. It's got this main lobe and side lobe components that we can see there quite clearly. Now what's happening here is the following. Now first of all, cast your mind back to the figure that I had up a few moments ago, which showed a sinusoidal waveform in the middle being multiplied by a rectangular window function at the bottom to produce a zero padded waveform at the very top. Okay. Now that process of multiplication, so we multiplied these 2 waveforms together to produce the top waveform. That process of multiplication in the time domain has a consequence in the frequency domain. And that consequence is, well, it's basically called convolution. So multiplication in the time domain is equivalent to convolution in the frequency domain. And when you convolve two waveforms, so if I was to convolve this middle waveform with the bottom waveform, what will happen is you will have the bottom waveform, the spectral shape that we have here in the bottom waveform will be repeated at each instance of a spike on the middle waveform. Okay, so because we have two spikes in the middle waveform, we will have two repetitions of this lower spectral shape at each of those locations. Now that is a simplified view of what's happening, but it should suffice to give you at least a decent grounding in what's happening with windowing. Okay, so let's just see if that happens. So I'm just going to zoom in on the very top here to see if what I'm suggesting actually occurs. So I'll just zoom in on the top. So what we can see is at minus 6.5 and 6.5 we've essentially got this lower spectral shape repeated. And what's key to take away from this short discussion is that the spectral shape associated with each of the sinusoids is influenced by the shape of this lower waveform, which is the magnitude spectrum of the window function that's used. Now in our case we first of all used a rectangular window function, but we can change the rectangular window function to another window function such as a Hamming or a Hanning and see what the effect of that is. Let's just go back into the script to do just that. Let me see, so I need to change a few things up here a little bit. I have a comment in here that I'm going to multiply, or I'm going to show the window function. First of all, I'm going to change it to be a Hanning window. Earlier up here I created a rectangular window function. Let's just comment that out. And what I need to do is also change this to x underscore zpad win, because at the earlier on I actually had multiplied my signal by a Hanning window. Okay. In fact, yeah, I'd just put Han win here instead. That would do the same job. What else do I need to change then? I need to change this to change the comment to Hanning window, and that should do for there. Let's just evaluate this piece of the code now. So from a time domain perspective, what's happening now is, again, still have my sinusoid, but this time I'm multiplying by a Hanning window. Okay, so there's my Hanning window to get this new Hanning windowed and zero padded signal. Okay, now let's just go back in here and let's take a look at the frequency spectrum associated with that signal. Let's put that should be now xcpad win, and that win is updated. That's fine. Okay, I think that's all I need to change. So let's select that code and evaluate it. There's the result. So once again, I still have, this is the double-sided magnitude spectrum of my sinusoidal signal, and if I zoom in there, that won't have changed. I still should see two spikes at 6.5 and minus 6.5, so zoom in there. Okay. Let's also zoom in on the double-sided magnitude spectrum. Well, that shouldn't be rectangular. I just didn't change a comment in my code. So let's just put that as Hanning. And let's just zoom in here. Now we can see that the spectral shape of the Hanning window has this shape here, and we can see it's got a wide main lobe and very small side lobes. And if I zoom in at the very top here again, what we'll see again, what's happened is in the frequency domain this middle waveform has been convolved with this bottom waveform, which basically results in this bottom waveform being repeated at each of the locations of the spikes. So if I zoom in here, I should see this spectral shape being repeated at 2 locations. And we can see that that's exactly what has happened. So this is basically all that windowing is about, and really if you know the magnitude spectrum, or sorry, if you know the spectrum associated with the window function, you will be able to predict what the spectral shape of sinusoidal components will look like based on this theory. Now what you need to appreciate is, of course, if I had more sinusoidal components present in the signal, well then I'm going to have more repetitions of this spectral shape. And if I have sinusoidal components that are close together, those repetitions are going to interfere with each other more and more. Okay, so that's an important point to note as well. Okay, so let's try to just appreciate where we are at the moment. So what I hope you're able to do now is appreciate why we get a very distinctive spectral shape, or why we get a particular spectral shape present at the location of each sinusoidal component present in a signal. Okay, but we've only really looked at this for a case where we've zero padded by a relatively large amount. What I'd like to do now is just take a look at the cases where we're dealing with signals that have been zero padded by a smaller amount, and we'll just go back into the script to do that. We'll just scroll down here. I've got some code that I want to run through. So what I've done is I've just zero padded the signal x by different amounts, 3000 in this case, 1000 in this case, and not at all in this case. And I've stored the results in these variables here. And the important thing to note is that the number of DFT bins in this case is 4000. The number of DFT bins in this case is 2000, and the number of DFT bins in this case is 1000. So in each case, the frequency resolution associated with this one is half of the one above, and again this one is half the DFT frequency resolution of this one here. So I'm just going to illustrate that anyway now. So let me just take this code and evaluate it. So we can see that we get this large value at 6.5 Hertz, and we still have the same spectral shape that we've seen before. We've got this main lobe centered at 6.5 Hertz, and we've got these side lobe components here. Okay, so each of the blue dots basically represents the value at a particular DFT bin. The blue line just basically connects each of the blue dots together. So let's just go back into the script now and evaluate this part of the code, which will plot the magnitude spectrum of the signal that's been zero padded by 1000 samples. And it's going to show that magnitude spectrum in red X's. And what we can see is that the red X's lie exactly on top of each a blue dot. So if I just zoom in there, we can see that red X lies exactly on top of a blue dot, and we can also see that every second blue dot corresponds to a red X. And in technical terms, what we're seeing there is that the magnitude spectrum of the DFT of the signal that's been zero padded by 3000 samples is a superset of the magnitude spectrum of the DFT of the signal that's been zero padded by 1000 samples. In other words, you can think of the lower frequency resolution DFT being a sampled version of the higher frequency resolution DFT. Okay, and we can see that again if I just go back into this piece of code and evaluate this part of the code, which just plots the magnitude spectrum of the signal which has not been zero padded, and it plots it in green circles. And we can see in this case that the green circles correspond to every fourth blue dot. Okay, and I'll explain why this happens in a separate video, but what you need to appreciate is this very important fact, that the lower resolution DFTs are all can be thought of as being a sampled version of the higher frequency resolution DFTs. And we can bring this point a bit further by considering the case where if you had a very high frequency resolution DFT, and by that I mean a DFT that's been zero padded by an infinite amount, then every DFT which is of a lower frequency resolution, or in other words, every DFT that's obtained by zero padding by small amounts, can be thought of as being a sample version of that infinitely high resolution DFT. Now, that infinitely high resolution DFT is essentially what's known as the discrete time Fourier transform, or the DTFT. Okay, so maybe just to highlight that, what I'll do is I'm just going to plot the magnitude spectrum of the zero padded signal. So there's the higher resolution DFT shown in black, and we can see that each of the lower frequency resolution DFTs are all lie exactly on the black line, and that just emphasizes this point that all lower frequency DFTs can be thought of as being a subset or a sampled version of the higher frequency resolution DFT. So the reason why I'm saying that is, once you know that fact, then you know that the shape of the magnitude spectrum is dictated by the higher frequency resolution magnitude spectrum that we started off with, and all lower frequency resolution DFTs are a sampled version of that higher frequency resolution DFTs, and that's why I started off with the high resolution DFT in the first place. So if you, for example, just focus in on the green dots there, that's the magnitude spectrum of the non-zero padded signal. And what I'll do now is, just to finish up, I'll plot that magnitude spectrum just on its own. So let's just go bigger, and we'll plot absolute FFT of X on its own. And there is our magnitude spectrum. It's got that shape that you can see associated with the green dots. Okay, so that's pretty much it for windowing. Thanks for your attention.